Okay, so wir haben nun 14 Uhr. Nochmals Hallo, grüß Gott in die Runde an alle heutigen Teilnehmer und Teilnehmerinnen zu unserem heutigen Webinar oder einem weiteren erneuten Webinar gemeinsam mit unserem Partner MG Chemicals. Hier denke ich im deutschen Markt noch nicht ganz so bekannt, aber das wollen wir natürlich mit dem heutigen Webinar ändern, spezialisiert auf hochwertige Anwendungen und Lösungen im Elektronikbereich. Und referiert wird es dann später von zwei Kollegen, Michael Strong und Robert Crosby. Also sprich, das Webinar findet heute in Englisch statt. Aber bevor wir dann ins Eigentliche reingehen, noch ein paar Worte zu unserem Haus, wer uns noch nicht näher kennt. Wie gesagt, Firma Tevipak. Wir sind in der Nähe von Stuttgart oder in Althengstedt, Nordschwarzwald zu Hause. Machen das Ganze mit 36 Mitarbeitern momentan und befassen uns eben mit der hochwertigen oder halt Vertrieb und Handel von hochwertiger Klebetechnik, leisten uns aber darüber hinaus auch eigene technische Berater, wo alle die Ausbildung zur Klebefachkraft genossen haben und auch ein eigenes Labor mit eigenen Techniker, wo wir jederzeit für Sie entsprechende Versuche durchführen können, wenn Sie uns Materialien, Substrate zur Verfügung stellen und oder auch gerne hier zu uns ins Haus kommen können nach Absprache mit unserer Technik. Weiter auch einen eigenen Showroom mit entsprechenden Dosiergeräten und Auftragegeräten, wo wir Ihnen jederzeit dann auch vor Ort hier präsentieren können, wie die Geräte zu handeln, letztendlich funktionieren. Ja, links in dem rot unterlegten sehen Sie unser Logistikzentrum, wo wir es in 2013 gegründet, gebaut haben, mit Stellfläche von über 2000 Quadratmetern, wo wir mittlerweile von der kleinen Tube bis hoch zu Fassware, Palettenware, IBC-Container unsere Kunden bedienen können. Auch seit vielen Jahren haben wir einen eigenen Online-Shop, wo Jahr für Jahr erfolgreich oder immer erfolgreicher funktioniert oder auch von unseren Kunden genutzt wird, vor allem für Kleinbestellungen oder wenn es um Bemusterungen geht, Testverklebungen geht. Wie gesagt, 24/7 Order-Management können Sie jederzeit hier nutzen für Bedarfe oder Kleinbedarfe, Bemusterungen etc. Und der letzte große Meilenstein bei Tevipak war im Jahre oder Ende Jahre 2022, dass wir uns nach 9120, sprich nach der Luft- und Raumfahrt spezifiziert bzw. qualifiziert und zertifiziert haben. Ja, wie gesagt, so kurz zur Tevipak. Dann würde ich jetzt gerne übergeben an die zwei Referenten von MG Chemicals. Michael and Robert, I will give you your presentation. It's now your stage, and please introduce MG Chemicals and your persons. And we are looking forward for an interesting presentation. And yeah, please start.
Okay, well, thank you for that introduction and good afternoon, everybody. My name is Michael Strong. I'm the Senior Technical Officer at MG Chemicals, where I've worked now for the past 12 and a half years. And the subject of our webinar today is to help you understand conductive paints. This is a very promising line that we have a lot of excitement over. And due to the capabilities of the products that we have, and the inherent market need for it, we thought we really want to present this and make everyone aware of what we have to offer. So it's a walkthrough of basically what its capabilities are, what are the different products that we have, understanding the features and benefits of the different products. So with that, let us get started. So rough outline for today, we start with the theory of electromagnetic and radio frequency interference. So if these products are solving a problem, we need to understand what that problem is. Once we have an understanding and appreciation of the problem, we can then present solutions. How do they work? What are the theoretical roots of the solutions that we have? We introduce a comparison of different conductive materials, but the focus today will be on electrically conductive paints. So I want to compare and contrast, but help you understand not necessarily the superiority of conductive paints, but how they are more applicable to certain situations that make them advantageous. From there, we break down the main components of a paint system, which is a binder or polymer system, as well as the conductive flake or pigment that is governing its conductivity. I want to help you understand why we've come out with multiple products rather than just one, and see how they compare and contrast so that you can understand where a certain product line is useful and where it has its constraints, and maybe where it's better suited for something else. Properties of conductive coatings is just a quick walkthrough of some of the key properties that we present on our technical data sheets. And it's to give you, from a first approximation perspective, an understanding of what they actually mean. So hopefully with that understanding, you can help decipher for yourself where a certain product is applicable and where it maybe falls short and we need to consider other materials. Applying conductive coatings is just the physical application of the coating itself, whether we're spraying, applying it on. We just go over some basic steps. These are also included in all of the technical data sheets that we provide for all of our products. So this is not just a catch-all for you to remember. We do give these instructions out on all the data sheets. And then finally, I want to present some common applications so you can understand where in industry these are being used. And then hopefully that should give you a better appreciation of what type of industrial problems these products are used towards solving. And then finally, a quick summary at the end. Okay, so we start with the theory of electromagnetic or radio frequency interference. And when we're talking specifically about urban centers, we can really think of them now as a soup of electromagnetic signals. Everyone has electronics on them all the time. And these electronics are emitting electric fields as they work. So that's essentially how electronics function, is that they send and receive these signals. But now these signals are everywhere. And also they're not necessarily restricted to their devices. They can travel out, especially when we're talking about radio frequencies. So the issue with interference is that if you have a device that is neighboring or nearby to your device, it can unintentionally pick up a signal that's being emitted from something else. And that can cause your device to malfunction, misfire, essentially interfere. And so this is the problem that we're faced with when we have so many electronics working all the time in very close proximity. And that is essentially what we're trying to solve with this line of conductive paint. Okay, so classically the solution is something called a Faraday cage, which is pictured on the right here. And the idea behind a Faraday cage is that it is an electrically conductive material. When an incoming signal comes, that signal stays on the perimeter of the cage. It's not able to penetrate the perimeter of the cage. It simply wraps itself around because it has a consistent voltage to do so. And it will continue to do so until the signal is grounded and no longer present. Now, if we house our electronics in something similar to a Faraday cage, that not only protects them from being interfered with, but it also contains the signals that are generated, emitted by the PCB within the Faraday cage itself. So now not only is it protected, but neighboring devices are protected from any signals that it will generate. And historically, the design concept towards this was, okay, well, let's use aluminum to house our circuit boards. But there's a couple constraints when we come up with aluminum. One is that it is somewhat heavy, and the second issue is cost. So designers instead switched to ABS plastic housing, which you can see on the left-hand side. The issue, of course, now is that these are non-metallic. So any kind of interference signal is going to go right through the plastic and interfere with the circuit board housed within. So we have to come up with a solution or a way to quickly and cheaply metallize the inside of the boxes themselves. And the most practical solution was electrically conductive paint. You can see our acrylic series line featured on the bottom there. Starting with the left, we have carbon. Next is nickel, which is that gray color. To the right of that is silver. And then finally, we have a copper solution, silver-coated copper. Now, these are typically painted on the interior of the box. You could apply them on the exterior, but when you do so, you expose the paint to any physical abrasion, chemical exposure, moisture, which can compromise its performance. So it's easier to do it on the inside where it's much more controlled and far less exposed. Okay, so just to go and get a bit more high level on how these actually work, if we sort of do a cross section of a conductive shield, what happens for the most part with these incident waves is that they are actually reflected off of the surface of it. That is the majority of how these perform. Some of the radiation will be absorbed and contained within the shield, but for the most part, it's coming directly off as by reflection. So the main point to consider there is that while you get a tiny bit of added benefit maybe from making the coating thicker, and we don't yet understand the magnitude of that, we'll probably be looking within the next few months as to the influence of coating thickness and how it affects the overall shielding performance. But for now, we know that it's fairly minimal. So the key takeaway here is that when you make your coating thicker, it's not necessarily a big value add. And these can be expensive materials. So it's something to consider as to whether you actually need a thicker coating in terms of the return on the investment that you will get from that. So the main thing I want to stress is that when you are applying a conductive paint, you want to make sure you get the full surface area. You do not want any parts that are not coated, because that is where radiation can leak in and out of. Now, how exactly do we go about measuring shielding performance? Well, there's a couple of standards. Now, it's important to note, though, that standards are just that. They are a way to standardize a measurement so that you can compare two different materials. It is not necessarily an accurate reflection of a real world application, because there we're dealing with not only different frequencies, but different distance to frequencies. How is the radiation emitted? Is it a radio wave? Is it transmitted through a coaxial cable? These are all variables that have an impact on real world shielding. What we present in our data sheet is standardized to a test standard, so you can compare our material with somebody else's. It's a good first approximation, but it may not necessarily reflect the performance you would see in the field. And so internal testing and validation is always required. Now, some of these standards include the IEEE 299, which is a very popular one. MIL standard 285 we've done in the past. These are very similar, so to talk about them, I can compare them sort of in the same vein. We show a cartoon of the basic schematic on the left there, where you have a transmitter on one end and a receiver on the other. Now, this is all occurring in what's called an anechoic chamber. And an anechoic chamber is simply a room that is designed to filter out any external noise. And by noise, I mean any electromagnetic interference. So it's very carefully engineered. They're also very careful in terms of any electronic sources to shield them with the sheathing on the wiring itself. So the baseline should be very quiet, very calm within an anechoic chamber. You take your transmitter. The transmitter is going to emit different frequencies of radiation. It does so at what is labeled the DUT, or device under test. Device under test is simply a panel that measures 2 feet by 2 feet. We apply our conductive paint. It's sealed around a gasketing material. And then on the other side, we have our receiver. The receiver measures the power signal relative to what the transmitter does. So the difference between the power of the transmitter versus what the receiver picks up, that difference is called the attenuation, which is the relative reduction in the signal strength. And that unit is measured in decibels. So on the right, you can see I've done a small chart, decibels versus the actual percent reduction. So if we measure 10 decibels, 90% reduction between the transmitted signal and the signal received. With most applications for RFI EMI shielding, a lot of customers along any frequency range want a minimum of 40 decibels. That's just common. Some people would want less, but we see it more and more is that we want a minimum of 40 decibel shielding. Some of our coatings at higher frequencies can do up to about 100 decibels. That's pretty premium performance. But typically you're somewhere between 60 and 100 decibels attenuation per our latest testing of the IEEE standard. Now, what are some of the advantages of conductive paint? And by that, I mean we're comparing them to other materials. So conductive foils, conductive sheets, conductive fabrics. First thing I want to mention is that with training, paint becomes very easy to use. And that's irrespective of your process, whether you're spraying it, applying it by roller, brushing it on. It does take a little bit of practice, and there are some key principles that we'll talk about later. But for the most part, once you are trained, a good operator can achieve very good precision and consistency with conductive paint. The next part is important, conforms to complex shapes. This is a drawback or a constraint that doesn't work with a lot of other materials, especially if they are a bit brittle or they have to be applied manually. To do so over complex geometries where there's maybe a lot of edges and corners, that material could tear, but it's also very labor intensive. Whereas with the paint, it's a liquid that is spreading and wetting over a surface area. So it's very good in that respect. And that ensures that we have complete surface coverage, which is very important to make sure we have no holes in our, essentially what is a Faraday cage. Durable and long lasting, similar to any interior paint you would apply in your house or commercial building. Depending on exposure, these paints can last 10 years, 15 years. In all likelihood, if you've done it right and chosen the right paint, it is going to last the lifetime of the electronic device itself, so it's not a liability. And then finally, conductive coatings can be scaled to production volumes quite easily. Again, it's a liquid, and you can simply just scale up the equipment to apply it so that it can be done quickly, relatively cheaply, and with high precision and minimal loss. Because these are expensive materials, you want to make sure you're applying them very efficiently. All right, so let's break down the basic components of a conductive coating. The first I want to talk about is the binder or polymer system. So you're probably familiar with different polymer systems available commercially. Acrylics. Acrylic is a material used in a lot of interior paints or nail polish. Epoxy we use as a more rugged coating system, say for concrete. And polyurethanes are used a lot in wood stains and paints for decking. So we've introduced those polymer systems in different lines of conductive coating, and I just want to run through a different sort of compare and contrast to help you understand where their utility best lies in based on their main features. So starting with acrylic, acrylic is our flagship line of conductive coatings. People like them because they're very easy to use. These are one-part systems that simply apply, and then their cure mechanism is physical drying. So if you do not have access to sophisticated oven or curing equipment, that's not an issue because these will cure at room temperature. They are reworkable, meaning they can easily be removed, and this can be done with common paint thinners, so that's easy enough to do. And from a perspective of conductive coatings, they have relatively high shielding when we compare them with other binder systems. We're not exactly sure why. This is just simply a test result. Its limitations are it's limited in terms of its adhesion. It's intended mainly for plastic substrates, and it has relatively poor durability. So it's really not meant to last in a harsh environment. And that can be simply places where there might be potential for physical impacts, or if there's chemical exposure, acrylic may not be the right choice for you. Compare that with epoxy, which is a very tough, rugged material. It is meant to go in harsh climates because it will survive. It has excellent adhesion to multiple substrates, including plastics, glass, wood, ceramic, composite materials, metals. So it's really a catch-all in terms of substrates that you can coat. And again, it has very high chemical resistance. These are two-part systems though, so they can be somewhat cumbersome to use. You have to pay special attention of how much each component, so it does require that you measure them out before using. Then there is the mixing process. And once you have mixed it, it's got what's called a working time. So you have a window in which you have to apply it, because afterwards it becomes too thick and no longer workable. So it does have a relatively long cure time, and it tends to have the lowest shielding performance. And again, we're not sure why. This is simply a test result, so we'll make you aware of that. And then finally, we have water-based polyurethanes. So we came out with the idea for water-based systems because a lot of people are painting interior spaces. This includes drywall for not only residential, but commercial office buildings. And the advantage of a water-based system is a couple things. One, it is non-flammable. So it's easy to ship, but it's also easy to store. You're not at risk of it catching fire and spreading. But it's also a water-based product, and it doesn't have any odor, which for a lot of users, that's a big advantage. So again, water-based for interior spaces, has relatively high shielding. Again, it is reworkable, so with paint thinner, you can remove it. And of course, it is non-flammable. But like with the acrylics, it has relatively poor durability, so we have to be careful about environmental exposure and whether it's going to work. And it does tend to have a bit longer cure time. Okay, so that's the polymer system that is governing a few key chemical and physical properties. But what about the electrical properties? Well, that is strictly governed by the electrically conductive flake we use. So in a conventional paint, you would use a pigment to introduce color. Here we introduce conductive metal to introduce conductivity to our system. So starting with carbon, carbon is a cost-effective solution for either very low frequency shielding, but it's for the most part used as a conductive coating. And remember, in that first slide we saw in the Hammond box is that black coating, that was the carbon coating. It's also corrosion resistant because it is a non-metal. So if you have environmental exposure to either salts or excessive amounts of moisture, carbon is good because it is not going to corrode over time. So its overall effectiveness is not going to be degraded by moisture exposure. Again, limitations, poor shielding at high frequencies. So above about 5 megahertz, it really drops off to where it's no longer effective. So as a high frequency solution, it really does not work out. And we're going to see that later in a chart that we present. Next, we have nickel. And with nickel, we're getting into what's called broadband shielding. So we can shield against frequencies from the hertz region all the way up to gigahertz. So it really works throughout pretty much every electronic which is operating within those frequencies. One of the key features, though, is that nickel is a ferromagnetic material. So we'll actually shield against magnetic fields as well, which the other conductive flakes are not. They are simply shielding against the electric field, whereas nickel does so against both the electric and the magnetic field. And we actually did test that in our latest water-based nickel coating, and we presented the data in the technical data sheet. One of its limitations is limited corrosion resistance. This does not apply to every nickel product. The nickel acrylic coating actually did quite well when we subjected it to corrosion testing, but the epoxy and water-based did not. We're not exactly sure why, but we saw a significant drop-off in terms of its conductivity. And when you see that drop-off in conductivity, that is going to relate to its overall shielding effectiveness. After that, we have AG copper, or silver-coated copper. So this is a copper flake that has a thin coating of silver over it. And that silver coating is meant to improve its corrosion resistance. It probably does so to a point, but really not much in a practical perspective. Again, this has broadband shielding, and the shielding is superior to that of nickel. So nickel is quite good. Silver-coated copper is better. So now we're really choosing systems based on its shielding potential. And of course, one of the main features is, despite the improved shielding, the cost is quite a bit less than that of silver. Limitations: poor corrosion resistance. So again, we want to avoid environments with a lot of salt, a lot of moisture, or even a lot of thermal cycling where we could see high and low temperatures, because that can induce condensation, which can then corrode the film. And then finally, we come to silver. Silver, in terms of performance, is pretty much unmatched. Superior shielding. It is relatively corrosion resistant. Yeah, it will corrode and drop off slightly, but it forms very passive oxide hydroxide layers on the surface, so the corrosion is limited, and it is still highly conductive. And we can achieve relatively low film builds in the range of 10 to 15 microns. So that will help you out a little bit, offset the higher cost. But of course, its limitation is the higher cost. If you want the performance, you have to pay for it. So we're very careful with recommending silver. It really is based on a need of superior shielding. Okay, so now let's look at some of the conductive paint properties. And again, these are presented in our technical data sheet, starting with the graph on the right. This is what we present to give you an overview of the shielding potential of the material. So we can see that these are presented as attenuation versus frequency curves. Remember, attenuation is the unit that we're measuring in terms of performance. So the basic takeaway is the higher the curve is up on the y-axis or attenuation axis, the better it is at shielding electromagnetic interference. And then as we stack them, and this is our acrylic series line, we can see that it lines up with what we had said in the prior slide. Carbon, again, really a big drop off once you hit 10 megahertz. 10 megahertz. So really above 5, you're not that effective. Around 5, you're still around 40 decibels attenuation. So it does work quite well, but beyond that, you see it drop off and really not be all that effective. The purple curve is nickel, followed by the red curve, silver-coated copper, and then finally silver. So you can see that, again, we're following a trend of certain metals just perform better than others. And these are what's dictating the decision to use one coating system versus the other oftentimes. So we need to know what frequencies our electronics are operating within. And then we also need to know if there's any strict attenuation requirements. On the left, we're presenting a basic depiction of what's called resistivity. Resistivity is a measure of a coating's conductivity. So we measure resistivity. Conductivity is the inverse of that. So the lower the resistivity, the more conductive your film is. And this is something that we present because, again, some people are using this strictly as a conductive film to move current from one place to the other. It's also a good quality control test that we will do for every batch of conductive paint, just to make sure that we have not only added enough conductive filler, but the conductive filler is still, it hasn't corroded or lost any of its properties. So we will run that through every test. We did a Tech Talk, which is a series we introduced a few years ago, presented on our YouTube channel, but you can access the video through our website. And it just gives you a basic overview of the resistivity measurement and how we go about measuring it here at MG Chemicals. Okay, so mitigating environmental damage. For a lot of the conductive fillers, I presented scenarios where the coating itself is liable to corrode over time, and that's specifically some grades of nickel and the silver-coated copper. Now, one of the options, of course, is not to use those conductive paints if the environment sort of dictates that it won't last. But there are strategies in which we can use them, and the easiest one to employ is applying a protective top coat. Okay, so this is just something that protects the underlying layer. That top coat does not compromise the performance of the conductive coating. What's going to happen is any radiation is going to pass through the protective top coat, but then as it hits our conductive coat, it's simply going to reflect off and then back outwards. So a lot of people think that would compromise the performance of the shielding material. It doesn't. So it's a strategy that some people can use. It is an extra step. It is an extra cost. So whether you want to actually implement that or not, that is up to you. With our acrylic and water-based series coatings, we recommend applying a water-based latex as a protective top coat. We don't recommend a solvent-based because, again, that solvent can attack the underlying film and potentially put some holes in the conductive film where radiation can leak in and leak out, so it could compromise your film. Whereas with the epoxy coatings, once they're cured, they're quite chemical resistant, so you can basically use whatever you want and not have to worry about the conductive coat being compromised. On the left, we're showing you a control sample from the ASTM B117 standard. For those of you that are familiar, this is a test standard for salt spray resistance. And it's not standardized in terms of any pass-fail result or time in which you immerse your samples. The customer can decide that. So we typically run these for a week, and we'll look at any weight gain, which you attribute to corrosive salt, but we'll also measure the conductivity before and after to judge how well it does, in fact, in the ASTM standard. Okay, so just a quick slide on a product to highlight the 841AR. This is very much a workhorse product for us because, again, the AR series or acrylic series of conductive coatings is easy to use, and it is very applicable to a lot of applications simply because, for the most part, it's in a controlled environment. You're simply applying a conductive paint in a place where it's not going to get a lot of exposure to anything that's going to degrade it. So acrylic series coatings are very good because they're easy to use and very robust packaging as well. You can see on the left, this is available as both a liquid and aerosol product. So it's very amenable depending on the scale of your operation, whether you're prototyping or going to production. We have the volume and packaging requirements to suit your needs. So with some of the key features and benefits of 841AR, and again, this is a nickel conductive coating, provides effective broadband shielding. And again, because it's a nickel product, it provides shielding against magnetic fields as well. Oddly enough, the 841AR had strong corrosion resistance. For some reason, the other nickel systems did not, but through the ASTM method, we found minimal impact on its conductivity. Available in liquid and aerosol formats, so we're accommodating for a lot of different volume scenarios. And it's HAPS-free solvent, which is just an added benefit. So it has a not so offensive smell to it, but it's also less restricted by regulations. And then, of course, we will do custom sizes available upon request. That's more of a business discussion to have with Robert, but that we are open to that. So now moving forward, we're looking now at paint application. So if any of you have painted in the past, this isn't a big shock to you. For the most part, we want to make sure to start that our surface is clean. Surfaces that are not clean, we run the risk of having the coating not wet out and spread over the surface area. And that's very problematic with a conductive coating because, again, we want to make sure the entire surface is coated so we don't have any holes in our Faraday cage. And so the easiest way to do that is with IPA or isopropyl alcohol. It's a great durable workhorse solvent, removes a lot of salts, a lot of oils, fingerprints, cutting fluids, stuff like that. So we give it a wipe down, make sure everything is clean. If we are going to apply, say, a water-based paint onto drywall, we suggest using a 10% tetrasodium phosphate cleaner. And that's similar to what you would do if you were applying a regular architectural paint. And remember, the water-based paints do not require use of a primer. You can apply them as a first coat and then simply apply an architectural paint over top of that. Dilution is often not needed. For the most part, these paints are sold in a viscosity that is ready to apply. However, you can apply thinners if you want to put a thinner coat down. So within our technical data sheets, we do have recommended thinners along with dilution ratios. Now, mixing agitation required to ensure homogeneity. This is very important because the conductive fillers that we use are very dense relative to the rest of the paint system. And what happens over time is that they will tend to settle out into the bottom of the coating system. So we need to introduce constant agitation to make sure that our mixture is completely homogeneous and to make sure that the coating that we are spraying has enough conductive filler to do its job. And then finally, any coating that's being applied by brush or roller, apply it like it's a regular paint. We suggest a horsehair paintbrush, which is similar to any paintbrush you would commonly use applying other paints. If you are rolling it onto a surface, just use a low nap roller. But for the most part, a lot of our customers will choose a spray application. It has better efficiency, it's faster, and it gives you a better aesthetic. Now, there was a video on the right, it doesn't play on this platform, unfortunately, that shows us painting a cover. But you get an idea of what the equipment looks like. So on the left there, that is an HVLP type gun, which you can buy at a hardware store, or there are specialty manufacturers that design and sell this equipment. That is a gravity fed system. And we also do provide instructions on how to set up that equipment for best results. What's very important is the one nozzle diameter, which we note at the bottom there. That is to prevent clogging because these do have conductive fillers, and we want to make sure that the nozzle opening is big enough so that it doesn't get clogged. The other is the spray pressure. If you go too high, you tend to separate out the two components of the paint, the binder and the conductive filler, and it does lead to poor results. And I've actually done customer site visits where the root cause of their issue is simply they use too much pressure. We prefer low pressure, and that gives you good wetting, but it also ensures your film is homogeneous. If you are to scale up and apply it via spray, you can use what's called an agitated pressure pot, which you can see on the left there. And these are systems that simply have two intakes for your air pressure. One is powering the spray gun itself. The other powers a small blade, which just spins around to keep your paint in constant circulation. Again, that's very important with conductive paints so that we don't have separation of our conductive particles. So with that, you can simply spray. The equipment itself will keep the pigment in suspension, so you don't have to worry about that. All right, so now we're moving on to some common industrial applications. This is lifted from sales reports of our customers and how they're actually using it. And hopefully it gives you some idea of what conductive paints are used for in the real world. So the first thing I want to mention is it replaces stamping or canning for package level shielding. So oftentimes now, because circuit boards are so small, miniaturized, and powerful, we have a situation where a component on a circuit board is interfering with other components themselves. And the solution classically was to put these aluminum stamps over top of the problematic chip to isolate themselves. Now that does add weight, but it is also actually not that easy to do. It does require specialized labor, whereas conductive paint is quite easy to apply. So you can localize it to a chip. Some customers, though, it's their entire circuit board is interfering with itself. So it's not practical to re-engineer it. Instead, what they will do is they will do something called board level shielding, and they will put an insulative coating down, and then they'll put the conductive coating over top of that. So the insulating layer prevents short circuits. And then the conductive coating is preventing chips components from interfering with the board itself. So we have had success doing that. Within the EV battery space, conductive coatings are used over the battery cells, and this helps to improve the charging and discharging performance. On the left there, that was a special application we worked on, and that was for a LiDAR detection system used in the self-driving vehicles. And that was for something that was basically improving the visibility for a LiDAR. So we applied one of our silver conductive coatings over something that was the size of a tennis ball. And remember that conductive coatings, their main mechanism on how they work is reflection. So what this was doing is the LiDAR was sending out signals and it was reflecting off of this tool, this apparatus, so that the LiDAR knew that there was something in front of it. So it's sort of communication through these reflective signals. So it's quite interesting. Shielding guitar cavities to prevent hum. This started out more as a hobbyist, but now it's sort of evolved into the designer phase for a lot of electric guitars. So there's a lot of industrial interest now in our conductive paints. And so they will coat the cavity underneath the pickup of an electric guitar, and that reduces that hum from the feedback that you get. So typically they will use our 841 water-based coating. They prefer water-based because of the smell and it's just easier to use. But you know, historically they would apply a foil, which was quite labor intensive and cumbersome, and now with conductive paint it's a lot easier to do. Shielding external signals from what's called ion mobility spectroscopy. These are used often in airports to detect contraband, but it relies on a very fidelitous signal from the instrument itself. And so you have to shield out all the external fields that are coming in through the electronics, people's cell phones, people's laptops. So we do have a lot of interest coating the exterior covers of these scanning devices. Not so much anymore, but classically these were used a lot on satellite dishes. And remember, conductive coatings, their main mechanism is reflection. So what it would do is it would help reflect signals towards the pickup of the satellite dish. So it would give you better signal fidelity. Tactical headsets for military use. Again, that's to prevent pickup of unwanted signals. So you simply have a very one-way communication. Conductive coatings onto satellites. This is a low Earth orbiting satellite. And this is a bit unique in that it is protecting the equipment from the radiation it's exposed to in space. And again, it's doing so because it's reflecting the signals away from the device itself. Replacing sputter coating for silicone wafers. Silicone wafers are sort of the birthplace of the components on a printed circuit board. And so classically they would sputter coat these to make them electrically conductive, and that could be with gold or carbon. That is an expensive and very laborious process. It's also quite slow. You can replace that by putting thin layers of conductive coating, so long as the coating is not only can be applied thin, is very conductive, but is also very flexible so that it doesn't shear and that you have good conformity to the part itself. End caps onto sonobuoys, which are used to detect submarines. So these work by sending out signals. And again, you want to minimize interference with anything external. So it's very important that you capture very fidelitous signals from the sonobuoy itself to the relay, not anything else that's interfering with it. Interior spaces like server rooms. So this could be just to prevent hacking or prevent just massive amounts of radiation from escaping the server room itself. So that would lend itself better to the water-based paint line. For the flooring, depending on what the flooring is made of, they may opt for the water-based or for the epoxy-based. Similar story for MRI rooms, which emit massive magnetic signals. So it's very important to contain that within the room itself. So a lot of hospitals will use our conductive coatings to shield their rooms designated for the magnetic resonance scanning. Okay, so to summarize, electrically conductive coatings suppress electromagnetic noise. They prevent neighboring devices from inadvertently sending signals to one another. Coatings are superior than other materials in conforming to complex geometry, providing durability, longevity, and can be easily scaled to production levels. MG Chemicals has extensive lines of acrylic, epoxy, and water-based conductive coatings to suit a variety of substrates and operating environments. Some of the key properties when evaluating a coating suitability for an application are the attenuation, and we did see that graph that I presented for the acrylic series, resistivity, and the overall durability is a catchphrase for what is the polymer system, how does it work depending on the stress it's going to be subjected to in its immediate environment. These coatings can be applied similar to conventional paints. For higher throughputs, coating can be applied by spray gun or used in an agitated pressure pot, so it's very easy to scale. And once you have that system sort of in place, you can do a lot of parts very quickly and very efficiently. And some common applications include replacing sputtering coating, signal amplification, guitar shielding, the charge-discharge for EV battery cells, amplification, reflection on satellite dishes, shielding a tactical headset, and anything that requires noise cancellation. Of course, that's the main thing that they are designed for. So that is all for me for today. And it looks like we will open the floor up to questions and answers.